Hi everyone, it's Michael. So I have another very great problem for you today. This is called the outer butterfly theorem. So a little bit different from the inner butterfly theorem, or just the normal butterfly theorem that I had earlier on my channel. But I guess it's similar in some ways because you're trying to show that the two segments are equal, and it kind of looks like a butterfly, I guess. So if you want to try to solve it, feel free to pause the video. Alright, so I'm going to go over the solution. So we have 4 points, A, B, C, and D, that lie in a circle. AB intersects CD at X, and then if you draw the line from the center O of the circle to X and you take the perpendicular, it meets AC at F and it meets BD at E, and we want to show that EX equals FX. So I'm going to actually show two proofs here. The second proof I'm going to give you is from one of my friends from Mexico, actually. And he said that in Mexico they really like projective geometry. And so his solution used projective geometry. And it's funny, I was talking to him, I feel like in America, I feel like I haven't heard as much about projective geometry. But yeah, apparently in Mexico they like projective geometry. So he found the solution pretty fast, and his solution, it's very short if you know a couple theorems about projective geometry, which I'm not going to prove those theorems in this video, but I'll kind of show you what they are to show you just how powerful projective geometry can be and how slick it can solve these problems. So the way that I did it, it's interesting. It's very similar to the way that I solved the butterfly theorem earlier, and the common concept that I've used in solving many different problems on this channel. So you'll see as I go over it. And it's interesting. I tried this approach a while back and I stuck with it for like 3 hours and I couldn't get it to work, and then I abandoned it. But then I went back to it and I found it solves the problem not too difficultly. So alright, so let's get started. So basically we want to show that EX equals FX. But one thing to note is that angle ABC is equal to angle ABBC because they both intercept the same arc. So therefore angle XAF has to equal angle EDX. So basically if you look at the triangles EDX and XAF, they both have a common angle, and we want to show that they also have a common side. But if two triangles have one of their sides has the same length, and an angle subtending that side is equal, then that means that those two triangles have to have the same size circumcircle. So if the problem statement were true, triangle EXD and AXF would have to have the same size circumcircle since these two angles are equal. Okay, so we want to try to show that, and I've mentioned this many times throughout my channel. So then the question is, can we maybe combine the circumcircles? Because right now they're not the same circle, they don't overlap, they're just the same size. But maybe we could try a trick to try to get them to overlap. And so that's exactly what I'm going to do here. So I'm going to let A prime be the reflection of A over OX. And you probably just saw the diagram jump. So yeah, so I don't even know how I did this, but so somehow the figure was at this stage, and then I moved point B and reflected point A over line OX, but for whatever reason, GeoGebra did both steps all at once. So it's not showing me move point B and then have point A prime. It's doing the two at once, which is very weird. So, but anyways, so I'll continue the problem with this configuration. So A prime is the reflection of A over OX, and so it has to lie on the circle. So why did I do that? Well, like I want to show that AXF and DXE have the same size circumcircle. So if I reflect triangle AXF over OX, then I basically want to show that that's triangle A prime XE, and that would have in fact the same circumcircle as EXD. So really I want to show that ED A prime X is a cyclic quadrilateral. That turns out to be an angle chase. So I'm going to draw in a few more points here. Okay, so if I can show that the opposite angles add up to 180, then that means it's a cyclic quadrilateral. So that will be my goal here. I'm going to try to show that angle ADE is equal to angle AXF, which is the same as saying that EDA prime and EXA prime are supplementary. Okay. But before I do that, note that XA is equal to XA prime by symmetry, because A prime is a reflection of A over OX. All right. And then that means that AA prime has to be parallel to EF, because OX is perpendicular to EF and OX is perpendicular to AA prime. So AA prime, so this is what I just said, AA prime is perpendicular to XO, so it has to be parallel to EF. All right, so now I'm going to get on with the angle chase that I mentioned. So angle FXA prime has to be equal to angle XA prime A, because they're alternate interior angles with these two parallel lines, EF and AA prime. So FXA prime is equal to XA prime A, which is equal to XAA prime, and XAA prime is equal to BAA prime, which is equal to BDA prime, which is EDA prime. So that shows that one of the angles in this quadrilateral, EDA prime, equals the exterior angle of the opposing angle in the quadrilateral. So EXA prime D has to be cyclic. And that's exactly what we wanted to show. So we said that if it were true that EX equaled XF, then it would follow that this quadrilateral is cyclic. We need to show the converse, essentially. So how do we go about doing that? Well, basically we wanted to show that we started out wanting to show that AXF and DXE have the same size circumcircle, but DXE and DXE and A prime XE have to have the same size circumcircle, because EXA prime D is cyclic. So basically, then we just need to show that EXA prime and AXF have the same size circumcircle, but that's essentially true by symmetry. So first, first I'm going to do another angle chase that essentially just reemphasizes what I said before. So EAX prime is equal to angle EDX, because we showed that this quadrilateral is cyclic, which is equal to angle BDC, which is equal to angle BAC, which is equal to angle XAF. So basically, if you look at triangles EXA prime and XAF, we want to show that they're congruent, but we know that these angles are equal, EAX prime and XAF, and we also know that XA is equal to XA prime, as mentioned in the beginning. So if we can show that one more angle is the same, then that would show that they're congruent triangles. And that's not too hard to show. So here's a little calculation showing that. So EXA prime is 180 minus A prime XF, but A prime XF has to equal AXE, and that's fairly clear because A prime XF is alternate interior with this, as I mentioned, XA prime A, and EXA is alternate interior with XAA prime, and these two angles are equal because XAA prime is isosceles. So 180 minus A prime XF has to equal 180 minus AXE, and that's angle FXA. So EXA prime is equal to angle FXA, and AX is equal to A prime X. And as I mentioned before, these two angles, FAX and EAX prime, are equal. So these EXA prime actually has to be congruent to AXF by angle side angle congruence. And from there, that solves the problem because that shows that EX has to equal FX. So this is the elementary solution that I saw. So now I'm going to go over a solution using projective geometry that my friend found, and it almost just kills the problem. So it really shows the power of projective geometry. It can solve problems in a flash with the right tools and theorems already in place. All right, so I'm going to go delete my proof, and so for his proof, I'm going to start out by letting BC and AD intersect at a point G. Okay. So now I'm going to delete some of the excess. So whenever you have this kind of a configuration where you have a cyclic quadrilateral and you draw the two diagonals, and then you let each pair of opposite sides meet at 2 points, there's a very useful theorem in projective geometry that says that the line GO has to be the polar of X with respect to this circle. So what is the polar? Well, I'm sorry, the line, not the line GO, the line between G and the intersection of these diagonals. So I haven't labeled it yet. The line GH is the polar of X with respect to O. So what the polar means, it means that it's a line that's perpendicular to XO. And the distance from O to that line, the perpendicular distance, if you take that and you multiply it by OX, it's equal to the radius squared. So it might sound like a kind of weird, arbitrary definition, but it actually turns out to be very useful in a lot of geometry problems. So this is a theorem. I'm not going to prove it here, but it's very commonly used. Whenever you have that cyclic quadrilateral, you take the intersection of the internal diagonals and the intersection of the pairs of opposite sides. It has to be the case that GH is the polar of X with respect to the circle. So in particular, it means that GH has to be parallel to OX, because that's part of the definition of being the polar. Okay, so that is my first step. And then there's another very convenient theorem in projective geometry. So I'm going to draw the line through X and H. So I mentioned this before, GH has to be perpendicular to XO because that's part of the definition of a polar. Sorry, one more step. So if GH is perpendicular to XO, then since XO is perpendicular to EF, GH has to be perpendicular to EF. So now I'm going to draw the line through X and H, and I'm going to let it meet side AD at I. And there's another very convenient theorem in projective geometry. Whenever you have, and in this case you don't even need any cyclic quadrilaterals, whenever you have sort of a triangle and you have 2 points on 2 sides of the triangle and you take their intersection at this point H, and then it intersects the extension of this side at G, and then if you draw the line through X and H and it intersects it at I, whenever you have this kind of a configuration, regardless of whether or not this quadrilateral is cyclic, it turns out that the cross ratio of G and I with respect to A and D has to be 1. So this can be proven using purely projective geometry. It can also be proven using Menelaus's theorem, but I'm not going to go through the proof right here. So we have the cross ratio of G and I with respect to A and D is equal to 1. So I described a few videos back what the cross ratio is, and also one of its properties. So one very useful property of the cross ratio is that if you take those 4 points included in the cross ratio and you draw the line through each of them in another point, so let's say H in this case, then if you take the intersections of those 4 lines with another line, then those 4 points have the same cross ratio as the original 4. So let's take the let's be H. Let H be the point that we connect all 4 of these points to, and let's see where they hit this line EF. So AH hits line at F, DH hits it at E, and IH hits line EF at X. Now where does GH hit the line EF at? Well, GH is parallel to EF. So in projective geometry, we basically say it meets it at the point at infinity. So it's almost like, imagine that GH were slightly tilted, not exactly parallel to EF, but just a teeny tiny bit tilted. Then it would intersect the line EF at a point very, very far on that line. So basically, and we call that very, very far point the point at infinity. So I'm kind of just being very informal here, but you can formalize. It is possible to formalize. So basically, the cross ratio of G and I with respect to A and D has to be the same as the cross ratio of, so like I said, G goes to the point at infinity, I goes to X, A goes to F, and D goes to E. So that cross ratio also has to be 1. So with cross ratios, you can do a little rearrangement. So if I just swap these 2 and swap the 2 points, it's not too hard to show that that gets you to the same cross ratio. So this infinity, really there's a point at infinity for every parallel line. So this is really the, or for every, for all the lines of every given slope. So this point at infinity, it's really the point at infinity corresponding to all lines which have the same slope as EF essentially, or all lines which are parallel to it. but just for convenience, I left that out of the notation. So what does this mean, cross ratio of f, e, x, and infinity? So we start with the segment FE, and what ratio does x divide that segment into? That would be fx over ex, right? And then let's say we take the point at infinity and we want to see what it divides that segment into. Well, if it's on line EF, but it's a point very, very far away, then if you take the ratio of the distance from that point to F and to E, it'll be really close to 1. So if you kind of take a limit here, you would get that fx over ex times that 1, so which is that ratio I just said, has to equal 1, and that proves that ex equals fx. So a little bit of theory in the second proof, but it definitely comes in handy. So if you're doing math competitions or you're just curious, I definitely highly recommend reading about projective geometry, because once you get a handle on it, it can be really fun. So I hope you all enjoyed this video. If you liked it, please give it a thumbs up. And if you want to see more like this, please subscribe to my channel. Thanks, everyone.